Okay, so hello everyone. I get we are all very hungry, so I'll try to be quick. I'm going to talk about 802.1x network access control and bypass techniques. So quickly, I'm Valérian Legrand. I work at Orange Cyberdéfense, previously known as Lexi. And just a few words about why this research. When we do penetration tests, we often ask the customers, also known as targets, to disable .1x protection so that we can be more efficient and to save time. And as time is money, especially for the customers, it's usually a good thing. But the problem is that this provides a good excuse for bad developers and admins to not see the facts in the report. For example, yeah, I know you found like 10 critical vulnerabilities on our systems and network, but we disable 802.1x for you, so it must not be that bad. Well, I got a bit tired of it, so I did this search first to try to educate our customers, and then to get a tool that could be used to show them that 802.1x protection is not 100% secure wall. So, yeah, huge thanks to these guys, which helped me a lot. And what are we gonna talk about during this presentation? We'll first do a quick overview of wired.1x protection, how it works, what are the different parties. We're not gonna talk about Wi-Fi today. Just quickly in the room, raise your hand if you've never ever heard about 802.1x. Great. So this should be quite quick, and we can go it sooner. Then we will move on to a brief overview of .1x bypasses and what is not .1x protection. And finally, we will talk about a tool that was developed during this research that is called Fenrir. And to be honest with you, I am bad at naming stuff, so excuse me. And finally, we will show some demonstration, because slides are not fun and videos are better. So, let's go. 802.1x standard is pretty recent in the history of network protocols, as it was created in 2001. And the goal of 802.1x was to provide physical port-based network access control. So basically, the goal is to authenticate new devices willing to connect to your corporate network, either through Wi-Fi, but here we are talking about wired.1x. In a typical .1x architecture, you have three different parties, three different roles that are involved. The first one is the most simple one. It's called the supplicant. Basically, it's just a new device willing to connect. When you plug your workstation on the wall, your workstation is the supplicant. When you plug a printer, it's the supplicant. So this will be the device that will authenticate itself against .1x protection. The second role is called the authenticator, and this is the most important one in a .1x architecture, as it will be the gatekeeper, meaning that the authenticator, and usually in a wire 802.1x architecture, it's a switch. This switch will decide whether your workstation will be able to connect, or you will just get rejected and you will cry all day. And finally, you have the authentication server, which is just there to validate your credentials, your password or your certificate. So, from an attacker's point of view, an external attacker's point of view, we will mainly focus on the authenticator role, as we don't have access to the authentication server. Oh, we shouldn't have access to the authentication server. So now that we know what are the three different parties involved, how do they communicate? Mainly, it's through a protocol which is known as EAP, for Extensible Authentication Protocol. EAP is just message formats, in fact, and there are lots and lots of EAP formats. The EAP is not sent directly on the wire. You won't see base EAP messages if you start a Wireshark and start looking what's happening. In fact, EAP will be encapsulating to create some kind of meta protocol that is called EAP over LAN, as we are talking about wired 802.1x. And the most known AAPOL protocol is PEAP, for protected EAP, which is the default one for Windows system willing to authenticate against .1x protection. So EAP messages are used for authentication between the supplicant and the authenticator, and between the authenticator and the authentication server. So basically, your credentials, your password, your certificate will be sent through EAP. Now, on the authenticator, on the switch, how does the switch reject or accept your connection? Well, the switch will define two logical states for each physical port. So when you plug your workstation on the switch port, the logical state will first be the uncontrolled state. In this state, the switch won't allow anything else but .1x frames to go through this port. You can try whatever you won't reach anything on the network. You won't even get a DHCP IP address. In fact, your supplicant here will just use a generic IP address that is defined in the standard. So when you finally successfully authenticate against .1x, the switch will then change the logical state of the port to that of the control state. And in this state, it's just like a normal port, in fact. You can do whatever you want, you can send whatever traffic you want on that port, and there is no .1x involved anymore. And keep that in mind, because this will be the main reason why we can still do something to access the network as an attacker, even if there is .1x protection in place. Just a quick note, even though once we are authenticated, the port switches to control state, the switch can periodically ask for re-authentication of the legitimate device, just to check everything is good. And, oh yeah, that's, well, we don't have time. Okay. I'm hungry. So, a brief overview of .1x bypasses. And first, let's just get things straight. 802.1x protection is not a magic wall that can protect you against everything, meaning that it's just a gatekeeper. If a legitimate device, your workstation, for example, gets compromised by, I don't know, that Nigerian prince, I'm sure you've seen it. If your legitimate device gets compromised, well, that sucks, basically, because 802.1x is not going to save your ass. In fact, when you are targets of social engineers, 802.1x is not meant for that. It's not meant to protect you against such attacks. And again, when your company allows bring your own device policies, 802.1x is not there to protect your devices. If one is infected at home, well, you can bring it inside the corporate network. It will authenticate against .1x protection, and the attacker will have a great pivot point to attack the rest of your network and your domain controller, for example. So now that we just set that aside, how can we really bypass .1x protection as an attacker? Basically, you have two solutions. If we can't access the authentication server, well, you have a third one, which would be to find credentials, but that's a bit too easy, so we're going to set that aside as well. So the first way, the easy way, is if you can find, as an attacker, devices, equipments that just does not support 802.1x standard. As I said, it's a pretty recent standard, so if your printer was created in 90, I don't know what year, it won't support the .1x protocols, so networks administrators won't be able to set that up for the printer or workstation or low-grade equipment, whatever it can be. I don't know, security cameras, for example. So if you can find a device that is either too old, low-grade, or very specific systems that can't be protected through 802.1x standard, then you can just unplug it, plug yourself instead of it, and you're done. You basically have an access to the network. And trust me, this kind of equipment, especially printers, you can find quite some inside corporate networks, especially for big companies. If you are a network administrator, you have a solution, which is called MAB for Mac Authentication Bypass. And yes, we put bypass in the name of a security feature, I don't know. But this solution was created by switches vendors, and especially Cisco, to protect devices that does not support 802.1x standards. So the goal here is not to authenticate the equipment through their credentials sent over EAP protocols, but through their MAC addresses, which is not that good of a security feature, actually, because you just have to spoof the MAC address of this equipment and you just get yourself inside the network. And usually printers and such equipments have their MAC addresses written somewhere, either behind or in the menus. Oh, and by the way, the MAB is, from Cisco's official website, the best security besides 802.1x to protect equipments. But okay, let's set that aside. So this is the easy way. You just come in, you unplug something that is not protected, you plug yourself in, and you're done. You can do whatever you want on the network. The problem is, well, you have to find the equipment, you have to physically unplug it, which is not the definition of stealth, I would say. So we will have to find another solution, which is called traffic injection. And from now on, in this presentation, we will mainly focus on this attack as it is one that is still valid today, that still works today, which is quite stealthy, but is a bit more complex to do. So, just a brief history. In 2001, the 802.1x standard is created. 5 years later, Steve Riley, which worked at Microsoft at that time, and maybe still working there, I don't know, managed to bypass 802.1x protection with just a single hub. Basically, he set up his hub between the legitimate device and the switch. And as the legitimate device was authenticated, the port was open, and Steve Riley was able to do whatever he wanted on the network. The switch didn't check where the packets came from. So following this attack, vendors extended the .1x standard to allow concurrent authentication sessions, meaning that, well, now the switch checks some stuff. So basically, if you are sending packets with a different IP address than the authenticated device, you'll get rejected, or the port will be shut down, depending on the switch implementation. So this effectively renders Steve Riley's attack inefficient. But in 2011, January and August, Ab from the Gremwell blog and Alva Duckwall created one tool and a script that improved upon the Steve Riley's attack to just add some spoofing features. Basically, now you still insert yourself between the switch and the legitimate device, but you spoof the legitimate device IP and MAC addresses, and it works. And it's still valid today. You can still do this today. And this is called traffic injection. So we will focus on this from now on. As I told you at the beginning of this talk, the goal was also to provide a tool that could be used, but in real penetration tests, real engagements. The problem with the Marvin tool, except that it's written in Java, is that it's more of a proof of concept than a real tool, meaning that in real engagement you lack some features such as reverse connections capabilities, which are quite often used in penetration tests, but we will come back to that a bit later. So this research led to the development of a tool called Fenrir. Again, don't blame me for the name. And the goal with Fenrir was to have a tool that could be used out of the box, meaning you don't have to modify existing attack tools such as Nmap, Netcat, Metasploit, I don't know, whatever. You can use them out of the box. Fenrir will take care of everything. And also, it's written in Python, not in Java, which is quite good, because we all know Java sucks. And you have some kind of features that have been improved by the tool, especially the reverse connection capabilities. And as it's written in Python, you can easily add stuff, add code, add your own modules to it. So the goal with Fenrir, but also with Marvin and the scripts that we saw earlier, is still the same. To bypass .1x, you have to make sure that frames at A, B, C, and D appears to be coming from or appears to be going to the legitimate device. So the attacker's machine, the attacker host, must not be seen on the network. There must not be an IP address, a MAC address that are sent on the wire that are coming from the attacker's machine. So basically, legitimate device frames are just forwarded one way and the other way around. But the attacker's frames are modified, are rewritten a bit like network address a bit like network address translation to make sure that the IP and MAC address of the attacker are not sent on the wire. So everything appears to come from to be coming from the legitimate device. So when you start Fenrir, the first thing that it will do is it will just let the legitimate device authenticate itself against the switch, because as you just unplugged the legitimate device to put yourself in between, the switch will ask for a new authentication. So you let the legitimate device authenticate. The switch port goes into the control state. And from now on, you can just do whatever you want to do on the corporate network. You manage to bypass .1x protection. You just need to make sure that every frame that are sent by the attacker's machine are rewritten so that the IP and MAC addresses comes from the legitimate device. So let's take an example that should be a bit more clear or clearer. I don't know. Let's take this. We have the legitimate device on the right, the attacker's machine in between, as I told you. We just unplugged ourselves. The legitimate device has done is re-authentication. So we're good to go. And now the legitimate device sends a packet on the network. Fenrir will just let it go through as it's a legitimate packet. We don't need to do anything. The IP address is already a good one. MAC addresses also. Fenrir will just take a look at the frame and store inside an internal table several pieces of information, such as the source IP address, the destination IP address, and source and destination ports. We will see a bit in a few seconds why. The answers come back. It's still for the legitimate device. We let it go through. Now, what if the attacker wants to, I don't know, contact a server behind the switch on the corporate network? The same happens. In fact, from the attacker's point of view, from the tool sending this packet, there is no change, absolutely no change. Fenrir will just capture the packet, still store the information inside the internal table. As you can see, we have the source destination, the source IP address, sorry, that is the rogue host IP address. But before sending it on the wire, we will rewrite the frames so that they appear to be coming from the legitimate device. And now, when the answers come back, we have a problem because the destination address is the legitimate device address. And so Fenrir needs to know where to send it. And this is where this table is useful, because now we have three pieces of information inside this packet that corresponds to an entry inside this internal table. As you can see, we have the IP address B and the both source and destination ports that match the packet's information. And so Fenrir will know that this packet is in fact not for the legitimate device, but for the rogue host, and it will rewrite the response again accordingly so that the packet is sent to the attacker's machine and not the legitimate device. In fact, at the moment, Fenrir just sends it on the loopback interface. And it works. The attacker gets its packet back, and the legitimate device still has its connectivity. And it needs it because if, for example, the switch decides that now it's time for re-authentication, we need to be sure that the legitimate device can re-authenticate against .1x protection. Oh, demonstration time. Yee. So this picture is just a picture of the lab that was used for the development of the tool. And as you can see, it would have been a bit complicated to have all the machines here for the demonstration. So excuse me, it's only gonna be videos, unfortunately. But you can also see in this picture that we have the legitimate device, the switch with 802.1x enabled, the authentication server, which is a radio server, and the attacker's machine running Fenrir is between the legitimate device and the switch. We also have a white Ethernet cable going to the left for the network. But the camera was really, really bad, so we don't have it. Okay, demonstration. If I can find my files again, yeah. Ooh. Nice. So we are on the attacker's machine, and we will start Fenrir. You can see that there is a beautiful ASCII art that was totally not stolen on Google. And we are gonna launch the auto-configuration module. So behind the scenes, we have the legitimate device that is re-authenticating itself against the .1x switch. And as it is doing so, Fenrir will just passively tap the traffic so that it can extract useful information that it will need to be running smoothly, such as the host, the legitimate host IP address and the legitimate host MAC address. And now we will run Fenrir in debug mode so that we can see a bit what happens. As it takes a bit of time, as I'm gonna quick this. It's very long. Very, very long. Here we are. So here, the legitimate host is sending packets. I don't remember what it was, but is communicating with something on the network. And as you can see, Fenrir is only forwarding the packets, as there is no need for rewriting anything. But still, Fenrir will learn from these packets different information that we saw earlier. In fact, it's just populating its internal table. And now we're going to try to, from the attacker's machine, access the network. And if we are successful, this means that we just bypassed 802.1x. So, just a basic netcat, hello world, seems okay. And so, we can send packets, but we can also get responses back thanks to this network's address translation that we talked earlier. So in fact, from now on, we can contact anything on the corporate network. We are already behind the 802.1x protection. So in fact, we've done it. We've just bypassed the 802.1x protection. And it wasn't that hard. So I'm sorry, but your 10 critical vulnerabilities are critical vulnerabilities. Even though he will try to say no, but it is. That's great. We managed to send hello world to a server behind the switch. Woohoo! Oh, I'm hungry. Sorry. But as I told you, we want to use the tool in real penetration tests. And sending hello world is not gonna do a lot for us in this context, so let's try to see what we can do more. I told you that in penetration tests, you often have to use connection. You often have to get back connections that are initiated from the network and not the attacking machine. And so Fenrir comes with a ruling system, a bit like IP tables, to allow specific protocols, packets to be forwarded not to the legitimate device, but to the attacking machine. This is especially useful when you are running fake servers attacking tools. Like, do you know about responder? Yeah, okay. We'll see this in a few seconds, but basically, if you have to start fake servers to capture anything, you will need to tell Fenrir that, for example, broadcast and multicast frames needs to go for the attacking machine and not the legitimate device. Otherwise, your tool will just do nothing. Also, this is very useful for reverse shells, which happen quite a lot in penetration tests, Metasploit, Netcat, whatever. And so Fenrir comes equipped with this. Also, Fenrir works at layer 2 and 3 because IP addresses and MAC addresses are rewritten. This means that anything that is above these layers can work with Fenrir. There is no need to modify anything else. Oh, well, bref. So in fact, you could use any tools that you can think of that use TCP, UDP, or whatever. Metasploit, CrackMapExec, PowerShell Empire, anything you can think of. And as I see you are a bit... just so, as you are a bit doubtful, let's just run this. And we will see that we can do what we would do in a real penetration test, such as port scanning with Nmap. So we have Fenrir running and we are gonna scan the .69 system. I didn't choose the IP address of this one. And it's starting. We can see that Nmap has already sent a few ARP packets that are being rewritten. And here we go. Nmap is going at it quite quickly. Fenrir will just process every packet. You can see that is rewriting the different IP and MAC addresses so that we still blend inside the legitimate traffic. And in the end, we should, if everything worked correctly, thank you, we should get our Nmap results back in a few seconds, hopefully. Oh, here we are. Okay, and as you can see, the scan was successful. We find quite a lot of open ports, to be honest, and it looks like we have a web server running because there are the 80 and 443 ports open. So let's run a quick wget command to check that. It looks like it worked. And as you can see, we get the standard IIS7 web page index. So we did it. We managed to scan a distant computer while going through the .1x protection and without the switch insulting us, which is pretty good. So we did a scan. That's great. It's quite useful for penetration tests, but this won't give us shells. So what can we do more? Could we get maybe a few credentials? Yeah. Come on. Okay, so rerun Fenrir again, and we will try to run the responder tool. Responder is a tool that will create fake SMB, LLMNR, NetBIOS servers to impersonate real Windows environment servers and try to capture hashes that are sent by Microsoft on the wire. So we add a few rules to capture this traffic, which are initiated on the corporate network and not the attacker's machine. We start Fenrir and we will start responder on another shell. Here we are. And we just have to wait for a credential to come back. And as we are with Microsoft, it shouldn't last long. As you can see, we got a hash, an NTLM, net NTLM, v2 hash for the 008 PC with the Fenrir user back, even though we are not authenticated against .1x. We don't have any credential, we don't have any certificate, but we still can run Nmap scans. We still can harvest credentials on the corporate network, even though we don't know anything about their .1x authentication. So, because I'm still hungry, a few takeaways. .1x protection is great. if you can implement it, do it. You'll have a hard time, but still try. It's very good. But just think that ways of bypassing it exist. You should not consider yourself secure just because you have implemented X2.1x. It's not the perfect magical wall that will protect your network. Think about that Nigerian prince we saw earlier. And that's it. Oh, yeah, on a side note, IDO.1x does not provide encryption for your communication. That's it. Okay, so you have the GitHub of the tool, which is not up yet because I failed to do it in time. But I will try to do it on Monday or Tuesday, depending on if penetration test happens at this time. But it should be up on Tuesday. Thank you, everyone. I hope. Thank you.